All right, why don't we get started? So we have homework due this evening at the usual time, 1 second before midnight. As I tell all my students, well, you're both in the other classes, so you both know. Don't wait to the last minute. And the clock is marked by the clock of the server and not the clock that you would have on your computer. There's some time skew between the two. So today we're going to continue on, and our focus today is going to be on considerations and the structure of error. And in going through this part of the discussion, we'll also augment our diagram and fill it out completely, the diagram for the anatomy or architecture. I think I used the word anatomy, for the anatomy of a learner. Okay, so where we last left off, we talked about this idea of using this simple, relatively weak linear model with something like PLA, and we can make modifications to make this thing much more flexible. And one of those things we talked about when we left off last time on Tuesday is we talked about this idea of computing a nonlinear transform from our original input representation. And here on the left, your left, in this left-hand frame, we have a two-dimensional feature space. And as you can see, the red points are not linearly separable from the blue points. And while certainly you could run something like a linear classifier using PLA to search through your hypothesis set, it would try the best it could and wouldn't do a very good job in trying to separate the red points from the blue points. And so, as such, certainly we know at this juncture that a linear model using PLA update to search through the set of hypotheses, it requires for the problem to be so-called linearly separable, right? Separatable, the +1 classes and the -1 classes, labeled data instances have to be separatable with a linear model. And so that's certainly not the case, as you can see here. If you imagine that origin is in the center of this rectangle, right? The horizontal axis would go from left to right in the middle. The vertical axis will go up and down in the middle, where the intersect would be at the origin in the center. If you look at the geometry of these points, the blue points tend to be closer to the center, whereas the red points tend to be further away from the center towards the edges of feature space. And so in that example, we applied a transformation or so-called phi function. In this particular transformation, it squared each of these features. And so it took x1 and turned it into x1 squared. And so if x1 were 2, x1 squared would be 4, for example, and also squared the second feature, x2. So this phi function brings our representation from the original representation into what we'll call feature space. Feature space is the resulting representation that you get as a result for computing some transformation on the original input representation. And if you think about what features are, right? Let's say if you're dealing with computer vision camera images, and let's say if you take your color pixels and you convert them to grayscale, right, to some black and white picture, as it were, you're performing some transformation, right? And so people call that features. Likewise, you could take an image and extract a representation of all of the edges in that image. Those are so-called edge features. They take a different form, but it's still the result of computing some transformation. And what any transformation does to the original input representation, it changes the geometry or the relative position or arrangement between the points. Now, in this particular phi function, this transformation, we transform from a two-dimensional feature space to another two-dimensional feature space. Now, this doesn't have to be one for one in terms of the dimensionality. The transformed version of the feature space can be a higher dimensionality or it could be a lower dimensionality. It doesn't matter. Okay? All right. Any questions about this? All right, so in doing this particular transformation, you can think of it as a polar transformation. It takes advantage of the fact that some points are closer to the center, to origin, in the original representation, closer than others, right? And so when we compute this transformation, as a result, we see that the blue points tend to congregate close to origin, and this representation would be down here in the lower left-hand corner, whereas the red points, inputs, tend to congregate further away towards larger values at the opposite extreme of this feature space representation. Okay. Any questions about this? Does that make sense? Okay, so let's continue on with this idea about nonlinear transformation and make sort of an accounting of the various components, what maps to what, because that's an important thing one would want to know. And so we start out with the original data in the first frame, upper left-hand corner. We perform our phi function to change the geometry, our nonlinear transformation. And this nonlinear transformation, for now, we don't assume that it's one for one. Your dimensionality in this new version, your transformed feature space, as it's called, can be higher dimension. In fact, when you do that, you get some nice advantages. You make it easier to separate the red from the blue, to find a linearly separable with a linear model hyperplane that can separate the data. And so you start with your original data and you get to a transformed version of the data. In the book, they call it Z space or feature space. And so for each point, little xn, that's vector valued in d dimensions, you have each x drawn from your possible set of data points, your in-sample points. You have a corresponding z sub n, which is the transformed version of x sub n. Okay, and so here you have z is the result of computing your phi function, your transform, on that original input representation in d dimensions, 2 dimensions in this example. So then, once you get your feature space, your transformed geometry, your feature space representation of the original input, then you train a classifier, right? And that's going to be a linear model in this feature space. So you can imagine now your learning algorithm, something like PLA, finding different straight lines that's trying to separate the red points from the blue points to, as closely as possible, coincide with a +1, -1 labeling assigned by the ground truth target function. And so in that third frame, you choose a weight vector, and that weight vector is called w tilde. And the reason why it's called w tilde is to represent the fact that this is the transformed feature space in which you're learning a linear model. And so you start out with a nonlinear mapping into feature space, and in that feature space, you create a linear model, right? And you're using that linear model, the weight vectors of which we're calling w tilde. Now, of course, that w tilde is going to have the same dimensionality as each one of these zn points in feature space. And so if your mapping goes, for example, from the original 2 dimensions to, say, 10 dimensions, right? Then that means your w tilde is going to be a 10-dimensional weight vector, and you're going to add your w naught to it. Okay? All right. Any questions about this? So now that you're in feature space, this is where you do the classification, right? And then you get a final best hypothesis. That final best hypothesis we'll call G tilde, and G tilde is going to accept some new input feature vector in feature space Z, and it's going to perform classification of that new point Z using W tilde transpose Z. Okay? Now, you can go back from this feature space to visualize or interpret what this decision boundary or what this final best hypothesis means if you were to go back into the original input representation. And so if you can perform the inverse of this phi function and sample along that best hypothesis in Z space and perform the inverse transformation, what you end up is what that nonlinear decision boundary equivalent would have been in the original input representation. And recall last time on Tuesday, we said something to the effect of what this nonlinear transformation phi gives you is the ability to separate or find highly nonlinear hypotheses, but you only pay the cost of training a linear model. And that's because you're doing it in this transformed feature space. Does that make sense? Any questions about this? So what happens then if you get a new input and you want to run this new input from an out-of-sample point X in the original representation? Well, you already know what phi is, so you take your point, you call phi on this new data point X, right? You know what this W tilde is, and so you just run that classifier, sign W tilde transpose phi of this new input X that was given to you out of sample when you encounter a brand new data point. Does that make sense? Any questions about this? No? All right. So literally, we have these steps here. We have the original data. We have our transformation into feature space or Z space. We train the classifier in Z space, and then we could invert uh, this brain fart, phi function, invert of a phi function in order to interpret what our results mean. Okay? All right. So let's take a look at these relationships. Here we have some x vector in d dimensions. And remember, we augment our x vector with x naught, so we have d plus 1 dimensions. We perform our phi function on that, and that phi function could be all sorts of things. It could be functions of individual features. It could be functions that involve subsets of individual features. It could be the identity function. It just propagates back that feature into feature space. All sorts of functions you can imagine you can use to get you from the original x space into z space. Now, we also have this z vector, and so each x vector in d plus 1 dimensions, as a result of applying this phi function, our transformation, our nonlinear transformation, you get some new dimensionality. Now, the dimensionality of each one-for-one respective point that's mapped through phi function from the original x input representation, it's going to have d tilde many dimensions. Now that's on purpose, right? D tilde could be equal to d, right? So that means the dimensionality doesn't change when you go from the input representation to feature space, or d tilde could be larger. That means you're going to a larger representation when you go from your original x input to your z space. And this d tilde, well, it certainly could be smaller. If you make it much, much larger, you're basically implementing a very highly nonlinear mapping from your original representation. And so the more or the higher the dimensionality that your phi function transforms each point into, you can almost think of that as a measure of the degree of nonlinearity that you've introduced by doing this transformation. And so here we have in bold an instance of an x vector, and we transform that into a feature space representation. And that transformation can either be contractive, reducing the dimensionality. It could be one for one, you preserve the dimensionality, or it could be expansive, meaning the dimensionality in feature space increases relative to the original dimensionality. And so for each input vector x, let's say we have big N many samples from our in-sample points, there's a one-to-one, well, I shouldn't say one-to-one, there's a direct correspondence for the mapping between each of those inputs x and its respective z in z space. And so you can think of, for example, z1 is the representation in feature space of x1. z2 is the representation in feature space for x2, and so forth. Does that make sense? All right. Now, the reason why I don't say one to one, because that has a strict mathematical meaning, because you could have two x's that map to the same z, right? That'll make inversion a lot harder, but that's certainly a perfectly valid transformation. So we have, for each x, we have its corresponding representation in feature space z, and then the original class labels from our original input representation, those class labels don't change, right? We're changing the geometry, but we're not changing the assignment of labels to inputs. We're only changing the representation and not the labeling, okay? All right. And so there's no weight vector for the hypothesis in X space. There is a weight vector in Z space because that's the representation in which we're learning the classifier, learning the hypothesis or searching for a final best hypothesis. And so for that reason, we say W tilde to correspond to each position of this weight vector in feature space. There's a weight for each of these corresponding positions in our Z vectors. Does that make sense? Okay. Any questions about this? All right, so then our final best hypothesis will be our G, and then to do the classification, we perform the sign W tilde transpose Z, but Z is just phi of X, okay? So if we get a new X, we just run our phi function on our X to get the equivalent Z representation, and then we just do the classification as we normally would, only using the weight vector from feature space. Okay, so, and oh, yeah, just forgot I had that slide. So our Z, if you evaluate it on a new input out of sample, it's just running phi on that example, and it's the same classifier that we've discussed before. Okay, so let's take a look at error, because as we talked about, error is our measure of coincidence between the ground truth target function's labeling of a point and the hypothesis's output labeling for a point. And we had this diagram. And again, for this diagram, the red boxes are things you have no control over. And we had introduced this idea of a probability over the features that are responsible for giving you the feature vectors. You have no control over that. And we had the hypothesis set, and we talked about the union bound as an extension to Hoeffding's inequality for the learning approach, where we consider more than one working hypothesis in trying to find ultimately final best hypothesis G, right? And given that union bound, we had an expression that considered the complexity or relative size of the hypothesis set as being one factor that you have to consider in order to get good coincidence between in-sample error and out-of-sample error. And so, what does it mean when we say we want our working hypothesis H? So, little h is just one of the hypotheses that you can get from big H, where big H is the entire hypothesis set. And so, what does it mean when we say little h, the working hypothesis, is equivalent to or approximately equal to our ground truth target function f? Well, we measured that using something we called pointwise error, right? And that pointwise error, or that error measure, was some notional measurement of the coincidence on all of our in-sample points between the current working hypothesis and the label assigned by the ground truth target function. And so we need that measure of error, and we get our input. And for each input, we have this expression for so-called pointwise error, right? Error contributed by that particular point. And so the error functions that we use for regression, we saw the squared error loss. And since the output and the label are real valued, we care about the magnitude, but not the direction, which one is bigger and which one is smaller. And so the squared error loss gave us a nice form that we can use in closed form with the derivative or gradient in order to find, using pseudo inverse, what the best W is for minimizing this squared error. And we did that over all of the in-sample points. We also, for the binary classification problem, we talked about this version of error. This is essentially an indicator function, I, and I returns 1 if the condition in the brackets is true, otherwise I returns 0. And so with a binary classifier, you're effectively looking at the count or the proportion of incorrect classifications, and you do that over all the simple in-sample points, and that's your total error, right? And so you have this idea of binary error for a classifier, and you also have squared error. Now, certainly, if you're doing error minimization, there's something called cross entropy error, but we're not going to talk about that now. And that's one way of doing measurement of error in a binary classification problem. And we'll probably more so mention that in greater detail when we read through the research literature towards the hopefully the final third of the semester. Okay, so we have these examples of pointwise error, and we take these pointwise errors, the error on a single data point in sample between the current working hypothesis and the ground truth target function. And so, of course, we do that averaging pointwise errors. We average them in order to get in-sample error. What is the average pointwise error over all of the in-sample points? And so in the case of in-sample error, we have our data points. They're discrete. And so we sum for n goes from 1 to big N, the pointwise error between the current working hypothesis evaluated on xn and the ground truth target function evaluated on xn. So that's for in-sample error. And we have that summation because you have a discrete set of in-sample points for your in-sample, over which you compute your in-sample error, and we take the average. Now, certainly out of sample, this is a theoretical construct. You don't really know what all of the different data points are. You know they're out there, and they're governed by some probability. And so we want the probabilistic average, if you will. And so for out of sample error, if we were to calculate it, we'd take the expectation with respect to the probability that governs those feature values that we can encounter. And so you take the expected pointwise error, measuring the coincidence between our current working hypothesis on that out of sample point X and the ground truth target function, the label that it assigns on that current feature vector X. Does that make sense? And so you'll notice the difference for the in-sample error, it's an average, right? For out-of-sample error, it's an expectation. Okay? All right. Any questions about this? No? All right. So if we were to augment this diagram, essentially I'm adding an edge here. There was one edge in the beginning, or in the previous version that I showed, from that probability distribution to the training examples. That same probability has an edge in the augmented diagram to this final best hypothesis. And that says that when you have your out of sample error, right, out of sample, the points that you run your classifier on, if you want good generalization, that the same probability that gave you the training examples should also be the same probability that gives you the out of sample points. Otherwise, it's just not going to work, right? So if you had a sensor, for example, and you are measuring something here at Dell State with that sensor, maybe it's a camera, and you're looking at the color of jackets people are wearing, and then you use that to gather your in-sample data. Now, out of sample, when you use it, let's say you went to a different school where perhaps the school colors were very different. Now, all of a sudden, it's not going to work well, right? And it doesn't work well because the probability distribution that gave you the training examples at DSU is not the same distribution that gives you the out of sample points when you go to that different school that has different colors. And that just says when you're trying to build a classifier, build a learner in general, if you want it to perform well out of sample, you want to guarantee or be relatively assured that the distribution governing the data on which you train should have some relationship to the distribution that governs the data that you get out of sample, right? Now, you might think, gosh, well, that seems obvious, right? But how might that appear in a real experiment? Say, for example, you're dealing with something having to do with temperatures, right? The temperatures that you see, if you were to compute a distribution of temperatures and you gathered that information in the summer, those temperatures are going to be very different than the temperatures in the winter, right? Because it's colder, at least here, North America, in the winter. So any learning model that you had related to temperature, if you trained it using data points collected from the summer, it's not going to work well if out of sample that was from the distribution of temperatures in the winter. So what do you do in such an experiment? Well, maybe you collect temperatures from all the 4 seasons, spring, summer, fall, and winter, and then you use it, and you can use it in any season, right? And so that begets, maybe it's experimental design, but at a high level, you really need to make sure that the probability distribution that gives you your training examples must be related to the probability distribution that gives you your out-of-sample points. In addition, suppose you stay in the northern hemisphere on the Earth and you measure temperatures at some latitude. What's it, longitude? No, which one is, that's latitude. Yeah, I think it's latitude. I always confuse them, but nonetheless, at some latitude, right? Some point north of the equator, right? And then let's say you want to measure temperature over all the 4 seasons. Let's say you're in some place north of the equator, and you want to build a classifier that runs on temperatures. So you collect data from some location, and if you're going to now deploy that application somewhere, it'll work well in another city that's at the same latitude, right? But if you say, for example, you collect data in the state of Massachusetts for all the 4 seasons for temperature, and then you deploy this learning system in Florida, it's not going to work well. Because yes, you're collecting over all 4 seasons, but the temperatures in Massachusetts tend to be colder all year round than they are in Florida because Florida is closer to the equator. And so that's another example where you really of being careful or mindful of the probability distribution that gives you your in-sample points versus your out-of-sample points. Because how can you learn on things that are completely wildly different from what you're seeing, right? You can't learn German and expect to speak French. It just doesn't work that way, right? Okay, for example. So anyways, when we look at these errors, not only do you consider the probability distribution, but you should also think about how these pointwise errors are calculated. And in this example, we're going to use the idea of a fingerprint scanner. And this is in the book and also on the MOOC videos. And in the system, you can imagine, you put your fingerprint down on something for verification. It scans your finger and computes or takes a fingerprint image. And the features in this fingerprint image, because everyone's fingerprint is unique, so too is this pattern of lines that make your fingerprint. So you could absolutely construct a representation that represents the relative edge orientations collectively for your fingerprint, right? What are the directions of all the little lines that make up your fingerprint? So then you put it into a classifier and it outputs +1 if it really is you, because maybe it has a database of all the fingerprints of people who are allowed to access some lock or resource, and it outputs a -1 if it's an intruder. So here in this table, this is often called a type of confusion matrix, but it's really a depiction of your pointwise error. And so along the columns here, we have F, that's our ground truth target function. And so a ground truth target function can output a +1. That means ground truth, you are the +1 class. Negative, it's the intruder. You are an intruder. It's not the identity of that particular person. Okay, and along the rows here, we have the current working hypothesis h of x. So if h of x outputs a +1, the classifier or working hypothesis thinks this person is you, a legitimate user of some resource who should have access. If h of x outputs a -1, then this current working hypothesis believes that you are an intruder and you will not be let in. So if we take a position in this 2x2 matrix and we first examine the diagonals, that's where everything is correct with respect to the target function. And so here in the upper left-hand corner, there's no error. What does that mean? It means that the ground truth hypothesis says, yes, you belong here, it's really you, but the predicted output, the current working hypothesis, says yes, it agrees with the ground truth target function. So it is correct. On the other diagonal, right, in position 2, 2, in this 2x2 matrix, we have a -1 for the ground truth target function, but we also have our predictor, our current working hypothesis, for that position in the 2x2 matrix, outputting a -1 as well. So it agrees. So the diagonal elements represent no errors, and typically for your pointwise error function definition, you'd have 0 cost, if you will, for these types of outcomes. There's no error. Now, what is of interest is anti-diagonal, right? So off diagonal here. So that would be position 2, 1 and position 1, 2. So let's first take a look at what happens down here, right? So down here, that's called a false reject. So what it says is ground truth, you belong, you should be admitted, but the current working hypothesis, h of x, says no, you are denied, right? So the current working hypothesis, h of x, has made a mistake. It denied someone who should have been granted access. Conversely, the other type of error here, it's called a false accept, a false positive, right? And what this means is that if we look at the ground truth target function, you should have been denied, but here, the ground truth hypothesis, or rather the current working hypothesis, it has given you access. So for that particular case, you should have been denied, but you were given access. Now, typically, for a binary classification, we would have zeros along the diagonal, but for the errors, and because remember, you want to minimize in-sample error, we would count this one as 1, and we would count the false reject as 1, and the false accept as 1. And of course, the goal is to minimize in-sample error. So you want to minimize both the false accepts and the false rejects, and when it's correct, that doesn't count towards in-sample error because it's 0 in both of those cases. Does that make sense? And so this is very application dependent because in that particular case, it's a naive case because it treats all errors the same. But depending on the application, and this is purely depending on the application, not all errors are the same. It means something based on your application. So let's go through some examples, and these are in the book. Suppose you have a big market, supermarket, whether Costco, supermarket, or whatever, and they have this customer loyalty program, right? And let's say, for the sake of example, they don't want to go to use cards because people misplace the cards, and they're going to use fingerprints, for example. Now, I know there are privacy issues, but just humor the example, please. And so you register with the supermarket, you register your fingerprint, and you buy your grocery items. You go to the checkout counter, and then you scan your thumb. And once it knows that you belong, it applies the discounts, and you save money, right? If you don't belong, you don't get these discounts. So let's take a look and think at the pointwise error function, and let's consider what you might or might not want to do for this particular application. So again, on the diagonals, we have 0 because it's correct. There's no error there. There's nothing to minimize. It already agrees with the ground truth target function, h of x. Our working hypothesis already agrees for those diagonal elements. Those are all trues. This is a true positive, and this is a true negative. But if we look off diagonal, here we have a false reject. Now, a false reject in this particular square, what happens? What does that mean? It means you are a member of this grocery store or shopping club or whatever, customer loyalty program, and you should receive the discount. So you come, you've been going to this store for a while, you scan your thumb, it says denied. You say, well, what's going on? I've been here for a long time, been shopping here, I should get this discount. So you try it again, denied. You try it again, denied. You keep trying, denied. And what does a customer do? They're unhappy. The customer's irate. And so what typically happens when you have a customer that's irate? If a customer is angry, they're no longer going to patronize that store because there are many other stores around that they can go. So, okay, Walmart is not going to honor the discount, so I'm going to go to Target instead. Forget about Walmart, right? That's what usually happens. Now, from a business standpoint, that's a very costly mistake for this classifier, right? Because what ends up happening is that you lose business. Somebody who was a loyal customer, because that's what loyalty programs are for your loyal customers who shop there a lot. So that means that person's going to no longer patronize that particular store and take their dollars elsewhere, and the store is going to lose money, right? And so that's a more costly error for the classifier to make. And that idea of a costly or more costly error is encoded by putting a larger number, your penalty, if you will, in that particular position related to that false negative, right? It's more painful to the classifier to make this type of mistake, to commit a false negative error. Likewise, if you look at the other position off diagonal here, that's a false positive. What does that mean? A customer walks into the store, grabs a bunch of items, and they start, shopping, and they say, "Oh, can you scan your thumb to get a discount?" They scan their thumb, knowing full well they don't participate in the loyalty program. All of a sudden, boop, okay, you get a discount. So the person who didn't belong to this membership for the customer loyalty program is thrilled, right? They're like, "Oh, great, this is wonderful. I get a discount even though I don't deserve one," right? Now, of course, that's neither here nor there, but that's not going to be detrimental or as painful, if you will, to the bottom line or the revenue of the supermarket or the store relative to the false negative. Does that make sense? And so when you consider what pointwise error means, you need to consider the two different types of error, whether it's a false positive or a false negative, and think on an application basis what that means to that application, because not all errors are equal for many types of applications. Does that make sense? Okay, so let's take a look at another example. And this other example, imagine you have access to sensitive records. Maybe it's national secrets, or maybe it's salaries of employees, or maybe it's just some sort of information access that you just don't want people to have access to if they shouldn't have access to that, right? So let's take a consideration for this idea of national secrets. Now, someone will scan their thumb to gain access to certain records. And those records could be accessible through a computer, or maybe there's a door to a room that has all these documents that they just don't want the average person to look at. So what happens there? right? Well, you have employees that work in an organization, and not all employees, for example, can access all the student records, right? It is a pretty sensitive thing to give people access to all the student transcripts and records and things like that. Not everyone should access that. So you have a bunch of employees, and only some of the employees are allowed access. So you have a database somewhere, and it says, okay, those people who should have access will scan their fingerprints, and then we'll recognize the fingerprints and either output yes +1, you should gain entry to look at this information, or no, you are denied, you should not gain entry to look at this information. So of course, if everything is correct on the diagonals, we have 0 returned by the pointwise error, right? So let's look at the off-diagonal terms for this case. Let's start out with the false reject. So what does the false reject mean? Well, the false reject means that somebody who is an employee and is in the database for access and should gain access, he or she scans the finger and the system says, boop, you're not allowed access. You're like, what do you mean? I should have access. I work here and I'm supposed to use this. I'm the registrar or something like that, or I'm, determining eligibility for scholarships, and I should gain access to these student records. But this system won't let me. So what do? You try again, and you try again, and you try again. But you're paid to be there, and you say, okay, I guess I don't have any work for this afternoon. I'm going to go home, right? But nonetheless, the false reject can be tolerated. The worst thing that will happen is that somebody who needs that information won't get it, but they're being paid to be there anyways. Or maybe they talk to a supervisor or something like that. But what happens in the false accept case? In the false accept case, there's somebody, maybe they don't even work there. They just go up to the door of this records room and just try their thumb on the door, and all of a sudden, click, it lets them in. So now somebody who should not have access to this information now has access, right? And for that reason, that particular mistake, the false accept, that error, that type of error, is much more painful to the organization because it now means maybe, credit card and social security information is now available to someone who shouldn't have access to that, right? And so for that reason, in this example here, the false accept has a much higher pointwise error than the false reject. And it's like orders of magnitude bigger to just note that this should almost never happen. And so what does that mean? It says when you're running your in-sample error, those false accept cases are going to influence in-sample error much more than the false reject cases. Okay? All right. Any questions about this? So what this means is that when you design your learner, not only do you have a method for determining your pointwise error, you also have to think about what those errors mean because not all errors will be the same for many different types of applications. Okay? All right. Questions? No? All right. Let me check the time. It is 5:12. All right. About half an hour. Okay. So when you measure error, it's the system user for your learner that determines the error measure, right? So let's say, someone asked you to design a custom learning solution for some domain. You learn about that domain, look at the data, do your transformation, design your learning algorithm, and you're ready to go. Now you need to sit down with your customer, so to speak, and say, gosh, well, tell me more about this application. What happens in this type of error? What happens in that type of error? And so it's the user of the system that influences what these different errors mean for your learner, right? Because I just showed you two application examples, and it means very different things for the same system based on the application. And so there are other methods you can use for setting your error measure. One can make simplifying assumptions for things that are plausible about your problem. And so when we talked about the squared error loss, that makes an assumption about how noise looks in your data, that it has a Gaussian distribution, right? You can also choose your error measure in a way that is very mathematically convenient for you, right? And so we also saw for the squared error loss, because it is smooth and differentiable, it made it easy for us to solve for the best hypothesis, that weight vector W, using the pseudo inverse. So another approach to choosing an error measure is say, I need to be able to solve it efficiently, right? So I'm going to choose a measurement of error that measures the coincidence between the current working hypothesis and the ground truth target function. I'm going to choose one that's mathematically solvable in a form that's really easily solvable, right? So maybe it's something that you can spread out in pieces on a GPU machine, or maybe it's something you can do sequentially, or maybe it's something that lends itself to a certain type of solution. Another one is maybe the particular form of in-sample error is convex. So now you can use a framework called convex optimization to solve for that W vector that minimizes in-sample error. And so there's all sorts of things you can do when you choose your hypothesis set and you choose your measure for in-sample error when you're training your learner. There are lots of things you can do when you're trying to craft an expression for pointwise error and in-sample error. Does that make sense? Okay. So let's now augment our diagram that we've been working with pertaining to the architecture or anatomy of a learner. We had the original pieces that you have no control over, the unknown target function. We had the training examples, and we also have the probability distribution over your features. And it's the same distribution that gives you your training examples is also the same distribution that gives you your out-of-sample points. And so we augment that diagram with the error measure, right? And this error measure straddles between the learning algorithm uses it, and the final best hypothesis G. And so it's that error measure that will give you a metric for the coincidence between the current working hypothesis, h, little h, and the ground truth target function f of x. And this error measure is very, very keenly involved in both how you wander or search for the hypothesis set, but it also will make life much easier if you choose it appropriately so that you get the right type of behavior out of your learner if you treat your different types of errors appropriately for your application. Okay? Any questions about this? Does that make sense? Okay, so this is we're almost finished with filling in the pieces for this anatomy or architecture of a learner. We'll shortly go to this idea of noisy labels. First, any questions about this? No? All right. So let's kind of discuss a caveat here. So the target function f, up to this point, we've been thinking of it as this, oracle that is always correct. But the target function is not always a proper function, right? It's not always a one-to-one correspondence in the mathematical sense of the word. It's not always a one-to-one correspondence between the labels and the instantiations of the feature vectors. You can have, for example, in the credit risk or the credit problem that we had talked about, you can have two customers that have nearly identical or completely identical information. Maybe both of them have the same salary, both of them have the same number of years in residence. For all intents and purposes, on paper, they look exactly the same. Now, certainly in a mortgage application, if somebody makes, say, $40,000 a year and somebody makes $40,000.50, they're the same, right? They're not exactly the same, but they're the same for all intents and purposes. You can have two identical customers, but one is a really good credit risk, always pays his or her bills on time, and the other one is a horrible credit risk, always misses payments. In that particular case, well, you have two feature vectors, x1 and x2, but x1 has a +1 label, and x2, which is the same feature values, has a -1 label. And so you need to account for those so-called noisy labels, right? You can have two different outcomes for the identical input. And in that particular case, how do you account for this as a machine as a learning algorithm? And how you do this is using a probability distribution. You'd have a conditional probability that will account for the fact that some proportion of the time for the same input, you're going to have a +1 label, and some proportion of the time for the same input, you're going to have a -1 label. Okay, so before we had our function, our ground truth target function, which again is still a theoretical construct, right? But it's out there. We need to model it. It's a deterministic function up to this point. but now there's a probabilistic aspect to it. So in order to account for these different outcomes of class labels that you can have on the identical input feature vector X, we need a probability. And so we use conditional probability to account for this. And so it's a probability of the class label Y, could be +1 or -1, given X, which is our input feature vector. So now, of course, we still have those label instance pairs. We have x1 and y1, x2 and y2, and so forth. And you can think now of those label instance pairs as being generated by a joint distribution, but there are two influences on that joint distribution. There's the p of x influence, which is the probability that determines the feature vector value. And then for that feature vector value, there's the labeling distribution, which is conditional. There's a probability that y is going to be +1 given that x, and there's a probability that y is going to be -1 given that x. And so given that, and mathematically, you can even think of when you multiply p of x times p of y given x, just mathematically using Bayes' rule, that is the joint probability, just by definition of what conditional probability means. And so we have these two influences, and we consider this p of y given x, that conditional probability, as the way we encode mathematically this idea of a so-called noisy label, right? In the target function, when you have similar values that have very different labels on them, you can consider that as being noise in the labeling function, okay? All right. So we have our noisy labels, and now what we enterprise to do is to basically learn what this target labeling function is, right? Because we want to know, okay, well, we can have a good credit risk who has the same value as a bad credit risk. How often of the time is it the good versus the bad credit risk, right? So we want to learn what that P of y given x is. And so our noisy target is really just a deterministic target plus some noise added, right? And so we can think of our target function as being the expectation of this y given x, so it's a conditional expectation, and once it selects a label, everything that's left over is the noise, right? Because it's a probability, well, one alternative, it could be the +1, could be the -1, one alternative is going to have a larger probability, right? Everything that's left over, once you subtract out that probability from 1, is going to be your noise. And so a deterministic target, you can even account for your non-noisy label case. Your deterministic target function y equals f of x is nothing more than this p of y given x that puts all of its probability on that particular label, right? So if you said f of x always labels a certain feature vector as +1, that's the same as p of y given x, where it assigns a 1.0 probability to the +1 alternative and a 0 probability to the -1 alternative. And so using this idea of a noise function, if you will, to talk about noisy labels, not only can you explain the deterministic target function that has no noise, but you can also account for or explain those cases where you do have noise in your labels. Okay? All right. Any questions about this? Make sense? All right, so let's look at the augmented diagram. And what changes here is this upper box. We no longer have just the target function. We have an unknown target distribution, and that unknown target distribution drives that target function, right? This unknown target distribution gives you an alternative on labels, so adds noise to the labels. And once you select a noisy label, the target function then assigns that label to that particular feature vector. That feature vector is given to you by probability P, and it's associated with that noisy label that was selected by the unknown target distribution, and then you have your label instance pairs, your historical records, as we had described before. So this is kind of like the precursor, if you will, to how you get labels, and it explains the notion that you can have noise in your labels. And again, you have no control. Same way you had no control over the deterministic target function, you have no control over this unknown target distribution. Okay? All right. Any questions about this? So this is the final version of our anatomy of a learner. And We won't be modifying this anymore throughout the course of the semester. And the beautiful thing about this is that when we get to the point of the semester where we discuss selections from the research literature, you'll be able to cast all this research or these instances of learners in this framework to understand the trade-offs that the authors of this or the experimenters have made. Okay? All right. So there's a probabilistic nature of X and Y, and our goal, as I said before, is to learn this unknown target distribution. You can think of this probability P of X as scoring the feature vector values as to their relative importance. And if you think about it, the important feature vectors are the ones that you see more, right? And so, for example, DSU, given the jacket colors, if you see a lot of, cherry red and Carolina blue together, well, those are more important because they have to do with DSU's colors, right? And so if a certain feature value is important, by definition, it's going to appear more, and therefore its probability is going to be higher. So you can think of this P of X as being a scoring mechanism that says the score is higher, the probability, if this particular feature value is more important than the others, right? So you have these two influencing factors. You have P of X that scores the importance of your feature vectors, and you have your noisy, unknown labeling function or noisy target distribution, and you're trying to basically what you're learning, you're not learning the joint distribution, you're trying to learn this unknown target distribution, P of Y given X. And so you can try to merge the two by saying P of Y given P of Y and X, but that mixes the two ideas together because you reuse this P of X when you're talking about your out of sample points. What you're really after when you're learning is to learn what this target, unknown target distribution is, P of Y given X. Okay. Any questions about this? No? Does that make sense? All right. So let me get more water. When we talked about is learning feasible, we talked about the relationship between in-sample error and out-of-sample error. Now, of course, for in-sample error, right, you have to take account for what the different types of error means to be suitable to your problem. We also talked about this idea of noisy labels, and that influences the error. And we want our final best hypothesis, G of X, to be very similar to, or equivalent to, or close by our ground truth target function, F of X. And so what this really means is that we want the out-of-sample performance, out-of-sample error performance for a final best hypothesis G to be 0. That's the ideal. But you don't know what out-of-sample error is, right? Because you don't know that probability distribution P of X. If you knew it, great, just model it and use it, right? But that's not the case in reality. So this idea can't be done in practice, but what we can do in practice is the following. Well, what we really want is there on the top. We want out of sample error for our final best hypothesis to be 0. That's perfect generalization. That's our goal. But we don't know what it is. We make use of Hoeffding's inequality that says if you set the right conditions, you have to maintain a balance between the error tolerance and the sample size and the size of the hypothesis set. And if you strike the right balance, the right context, the right conditions, you can guarantee that in-sample error, which you have control over, both with the types of errors as well as the form, and you can make it a mathematical form that's convenient to minimize, all sorts of wonderful stuff. But if you can set the right conditions for in-sample error, that means out-of-sample error is not going to be that much different from it. And that's what Hoeffding's inequality and the extension of Hoeffding's inequality, the union bound, guarantees us. That's mathematically sound. And what you do have control over, setting the context right, or the right conditions, out-of-sample error that you don't have control over and you don't know, it'll be close to in-sample error. But what you do have full control over is how you pose this in-sample error, right? You can choose the right learning algorithm to search the right way through your set of hypotheses. You can choose the size of the hypothesis set. You can even choose the way your errors are expressed for that particular problem to best benefit the problem. You can choose to do classification. You can choose to do regression. You can do pocket PLA. You can do a nonlinear transformation. You can use regression and pseudo inverse to bootstrap what your initial W is and just do PLA after that for learning. All sorts of stuff you can do. So in order to learn well, you need to do these two things. You have to ensure that out of sample error is close enough to in sample error. You have to set the right context, make the right trade-offs that you satisfy the union bound of Hoeffding's inequality, right? That's the first thing. The second thing is trying to make in sample error as small as you can. That's the minimization problem. So you set the context so that E out will be close by, and that's guaranteed mathematically, and then you make E in as small as you can. You do those two things, and you will have a very good learner. Okay? So, but there's a problem here. The problem has to do with this idea of M, the complexity of the hypothesis set. And as we talked about with the union bound or Hoeffding's inequality, this M could completely overwhelm the negative exponential, right? Completely overwhelm it. What does that mean? It means if your hypothesis set is too complex, that means your in-sample error and out-of-sample error are going to diverge from one another. And you'll actually violate this first point about E out of your best hypothesis being close to E in of your best hypothesis, right? So there's this other part about setting the size of the hypothesis set. So you have to make the right trade-off, right? Your hypothesis set has to be complex enough for E in to be small, but it can't be so complex that you lose track between the difference of E in and E out, right? And so when we talk about regularization, we'll talk about a very elegant mechanism that tries to balance this trade-off, simplicity against E in being small. Because just by making the second point valid, E in has to be really small, you could make your hypothesis set so complex, it's going to memorize the samples, and it's going to be 0, En 0 all the time. But if you try to satisfy point 2, you're going to violate point 1 if the size of the hypothesis set is too big. If you try too hard, as it were, to make hypothesis set too small, well, En is going to be bigger because it's too simple to describe what's happening in your data, right? So how do you strike this balance? That's the subject of regularization. So this last graph, this talks about the trade-offs that we have, and this horizontal axis in this plot talks about the complexity or the simplicity of your hypothesis set. As you go to the right in this graph, this quantity VC dimension, it gets bigger and therefore corresponds to having a more complex hypothesis set, right? As you go to the left in this graph, that talks about a more simplistic hypothesis set. And so here we have a bunch of plots, and you can see in-sample error. In-sample error gets smaller and smaller and smaller as you increase the complexity of the hypothesis set. And the reason for that has to do with its ability to describe the data, right? We saw when we went to a highly nonlinear hypothesis set, right, through this phi function, right, we were able to carve out things that were circular instead of just straight lines. A circle is more complex than a line, has more parameters, right? And so if you make your hypothesis set very complex, you increase your complexity, in-sample error is going to get smaller and smaller and smaller. Now, certainly, we see here out of sample error, it gets smaller and tracks with in-sample error, but only up to a certain point. Now, after a certain point, in-sample error continues to get smaller, but out of sample error starts to diverge. That's when you start to memorize the data and not generalize well out of sample. Now, that point where the out of sample error diverges, it has a name. It's called overfitting, and we'll talk about that in great detail. And so what you really want is you want this stopping point that says, I want in-sample error to track well with out-of-sample error, and you notice they're doing that as E in gets smaller, E out also gets smaller, but you want to stop right when E out starts to diverge, right? Okay, and so we're going to talk about this in a very formal theoretical way, and we're going to develop this notion of the VC dimension, which is a single quantity that represents the learning power, if you will, of a learner, right? And it's a single number, so now we can compare learning methods and say, is this one more powerful than that one? And we'll also learn what the cost is for a more powerful learner, right? Of course, it has to do with the data, but there are a couple other things, loose ends that we need to tie up. And so this VC stands for Vapnik Chernovenkis. Vladimir Vapnik works at Princeton University. I think he's still around at Princeton. And Chernovenkis, I don't remember who Chernovenkis is, but that's the other scientist who developed this framework. And so in machine learning, we have our own computational complexity measurements, just like how the algorithms folks do. So in this graph, we also have model complexity. So as model complexity increases, in-sample error decreases, it tracks with out-of-sample error because you're within the bounds of the context that's Herfting's inequality and the union bound satisfy, and all of a sudden, in-sample error continues to get smaller while out-of-sample starts to diverge, okay? And so this VC dimension, dVC, is that number that corresponds to when that inflection point starts to happen, okay? And that's a depiction of the relative learning power, if you will, of a particular learner. So generally, if model complexity increases, gets bigger, in-sample error goes down. And we see that with the blue curve. Likewise, if model complexity increases, generally E out minus E in, how much they diverge, excuse me, is going to get bigger and bigger. So here, they're tracking, but you notice that track is starting to get bigger and bigger and bigger. And once you get here, that track really starts to diverge from one another, okay? And so with regularization and VC dimension, we'll talk about not only the power, but also how you can control that trade-off between make it simple enough, your hypothesis set, that E in and E out are close to one another, but not so simple that E in is too big. Okay? All right. Any questions about this? Does that make sense? Okay. So that's the last slide I had. It is 5:35, and we'll just end 10 minutes early. I look forward to your submissions tonight on Blackboard, and I will see you both on Tuesday.